Friends, welcome to the 46th lecture, where we will continue with the blast resistance. We will discuss more in detail about the various type of blast loads estimated from overpressure as the blast wave propagates and the structure interferes in the propagation path of a blast wave. We already said in the last lecture that front wall load depends upon the impulse, where the impulse is given by half PR minus PS of TC plus half PS of TD. I call this is equation 1, let us say TD, where TE is the given by 2 IW by PR, which is also equal to TD minus TC by PR of PS plus TC. So, we said that in the pressure time curve, if I say this is my PR, which has got a loading feature of this nature, where we know this is going to be TC and this is going to be TD. We know that this is my PS. We make an equivalent loading from this bilinear curve, and we call this as equivalent period and we call this as equivalent triangular loading, which is going to act on the front wall, which is based upon the impulse given by equation 1, which we saw in the last lecture. We also said in the side wall, because of the attenuation effect, the overpressure effects will be lesser than that of the front wall. And if you look at the pressure time diagram in the side wall loading, you know the pressure will rise, go to its peak, which we call as peak pressure, then it drops, and this time of rise is called TR, and of course, this is T0, where the rise time TR is given by BL by U, and the overall duration TO is given by TR plus TD. Let us now move on further to find the roof load due to shock wave propagation cost from the blast wave. If the building module or any living quarter item on the topside facility of offshore platform has a flat roof, it does not cause any deflection, because essentially blast wave travels horizontally. Therefore, the roof will effect or feel the roof will have only the side on overpressure effect, which will be now combined with the dynamic wind pressure. This will be more or less similar to that of the side walls. We all agree that the dynamic wind load acts on the roof which will be in opposite direction to the normal overpressure load. The roof loading also depends on certain factors. It depends upon the ratio of blast wavelength to the span of the roof member. It also depends upon the orientation with respect to the direction of propagation of blast wave. The fourth element is the rear wall. The rear wall load is generally used only to determine the overall effect of the blast wave loads. Actually, the rear wall load tends to reduce the overall blast force. It is important to note that blast wave loads are direction dependent and no parallel directions are considered simultaneously. In that case, we agree that load on rear walls are generally neglected in the design blast wave loads. The primary reason is rear wall load lags with respect to the front wall by ratio of BL by U. We know that BL by U is actually the rise time. When you calculate it for the side walls. So, according to TNO Green Book, the rise time of the positive phase will be 4s by U. The total duration will be considered as Td and hence Tr is actually BL by U plus 4S by U, and T0 will be TR plus TD. I call this as equation number 5. So, if you look them graphically in the pressure time representation, the pressure rises, then it drops. We call of course this as rise time, and we know this is going to be equal to BL by U. We already said that. So, this is TR, and of course, in this case this is going to be PB. I am talking about the rear load. This is according to T and No Green book. Alternatively, you can also estimate this load using UFC 340.02. According to this, the graphical representation of the load in pressure time curve will have rise period and the drop, and of course, we know this is TR and this is given by BL by U, and this is PB, and in this case the positive phase rise time is actually only S by U. The total duration is TD and the rise time is BL plus U by S by U, and overall time is rise time plus duration TD. So, UFC 340.02 2008 structures to resist effects of accidental explosions, unified facilities criteria UFC, United States Department of Defense, Washington DC, year 2008. If the system is of a network of beams and columns, what we call as a frame building, then frame will experience diffraction loading. Which will be actually equal to the net load that occur on the front and the rear wall of the building module. So, this net load also accounts for the time or the phase lag. During the time when the blast wave travels from front to rear of the building module, the frame will be subjected to large horizontal unbalanced pressure on the front wall, and we agree that the load on the frame will be actually the net load on the front and rear. After time lapses, and the blast wave propagates, front wall load is partially offset by the rear wall load. So, graphically, if you try to plot in the pressure time plot of this variation, let us say load on the front wall is plotted like this in red color. Let us say this indicates load on the front wall, and of course, this value is P r, and this is indicated as T c. Let us extend this, and this value is P s plus C d of Q 0, which we already explained. Further, let us try to see the load on the rear surface. So, this will have a magnitude which will be indicated in green color. So, this is load on the rear wall. We know the net effect of these two is what we are looking at as the load on the frame. We know that this value is B L by U. So, we are now looking for a net loading which is indicated by the hatched portion. So, this is the net load which is acting on the frame. The next factor is the negative pressure, because we know as the blast wave propagates, it reaches the peak, then dips and then comes to normal. So, there is a negative pressure which is called the suction pressure, and this will have a rebound loading. Due to negative phase of the blast wave propagation in passage of time, the building module will experience blast load effects in the opposite direction to that of the primary load. Okay, that is very important. It experience blast load effects in the opposite direction to that of the primary load. This is what we call as a rebound effect. This will be dependent on the inertia effects of the peak over pressure load. Fortunately, the negative pressure forces are ignored, as they are generally insignificant. The next effect what we have is leakage pressure. Openings present in building modules like doors, windows, vents, etc., will enable expansion of blast loads. This is what we call as leakage pressure loads. When the blast wave expands through the openings, pressure level drops. This results a sudden expansion inside the confined space of the building module. Let us take an example and try to work it out. The design blast wave. So, let us say compute the blast load on the building module of an offshore platform subjected to blast wave traveling horizontally. Let us say I have a building module which is 20 meter wide and 30 meter long, and about 5 meter high. Say this is 5 meter high, this is 20 meter, and of course, this is 30 meter. So, I call this as BW, this as BL, and the blast wave is hitting the system from this direction, traveling horizontally. So, it is very clear that from this figure, please note blast wave is applied normal to the longer side of the building, and the peak overpressure with the duration is actually 40 kilopascal. The duration is 0.05 seconds. So, the peak side on overpressure is 40 kilopascal and the duration is 0.05 seconds. So, let us say shock wave parameters shock wave velocity u is given by 345 1 plus 0.0083 PSO raised to the power of 0.5. So, u is 345 1 plus 0.0083 into 40 raised to the power of 0.5, which is 398.172 meter per second. Once I know this, I can find length of the pressure wave, which is LW, which is given by u into Td, which is 398.172 into 0.05, which is 19.09 meters. The peak dynamic wind pressure is Q naught given by 0.0032 of PSO square, 0.0032 of 40 square, which is 5.12 kilopascal. The second one is to compute the front wall load. To compute that, let us first find the reflected overpressure, which is controlled by a coefficient CR, which we know is given by 2 plus 0.0073 PSO. Let us compute that by multiplying the known PSO value for the given case. Now, the coefficient to be multiplied is 2.292. Therefore, PR is CR into PSO, which is 2.292 into 40, which is 91.68 kilopascal. Let us say the clearing distance. The clearing distance we need to calculate, for which BH height of the module is 5 meter and BW by 2 is 15 meter. We know that the clearing distance S is the least of BH and BW by 2. So, therefore, S is 5 meters. Now, I can find the reflected overpressure clearing time, which is Tc, which is 3S by U, which is 3 into 5 by 398.172, which is 0.0376 S, which is less than Td. The drag coefficient, we take it as 1.0 in this case, and the stagnation pressure is given by Ps is equal to Pso plus Cd into Q0. In my case, it is 40 plus 1 into 5.12, which is 45.12 kilopascals. Therefore, the front wall impulse IW is given by 0.5 of PR minus PS of Tc plus 0.5 of PS into Td, which is 0.5, 91.68, that is my PR, and PS is 45.12 Tc, which is 0.0376 plus 0.5 into 45.12 into 0.05, which tells me the impulse is 2 kilopascal second, so many seconds, and the effective duration Te is given by 2 IW by PR. So, in this case it is 2 into 2 by 91.68, which is 0.0436 seconds. So, I can try to plot this on the pressure time graph. So, this is my time, my pressure in kilopascal and time in seconds, my plot, and this is my 45.12, this is my 0.0436. This is for the front wall loading. Let us talk about the sidewall loading. For the sidewall, drag coefficient Cd is minus 0.4 as a given data. The equivalent load coefficient for the sidewall is actually dependent on LW by L1, which is 20 by 0.3, which is 66.667. So, the equivalent peak over pressure for the sidewall, which is Pa, is given by Ce into Pso plus Cd into Q0. So, equivalence in this case is going to be 1 because of the ratio, plus Cd is minus 0.4 into Q0 is 5.12. We know that the sidewall will have a lesser effect than the front wall, okay, which is going to be 37.952 kilopascals. Now, let us compute the rise time, which is Tr, which is L1 by U, which is 0.3 by 398.172, which is 0.0007 seconds, and the duration Td is actually 0.05 seconds. Let us try to plot this in the pressure time scale. We know that this is going to be 37.952 as you see here, and this value is going to be 0.05 seconds. This is for the sidewall. Let us work out for the roof load. To estimate the roof load, we need to consider a strip. Let a strip of width 0.3 meter and length of 2.4 meter is considered, because that is going to be the modular dimension of the roof member. So, now in this case L1 is going to be 2.4 meter and drag coefficient for the roof is CD is minus 0.4. Equivalent load coefficient is actually the ratio of LW by L1, which is 20 by 2.4, depends on this ratio, which is 8.333. For this ratio, you can refer to the UFC chart. One can find the equivalent coefficient as 0.9. So, therefore, equivalent overpressure, that is peak overpressure, is PA, which can be CE into PSO plus CD into QO. CE in this case is 0.9, PSO is of course 40, CD is minus 0.4 and Q0 is already estimated as 5.12, which gives me 33.952 kilopascal, which is much lower than the pressure on the front wall. So, the rise time for this case is going to be TR, which is L1 by U, which is 2.4 by 398.172, which gives me 0.006 seconds. Time of duration of the loading, which we call as TD, is 0.05 seconds. So, therefore, the total positive phase duration which I call T0 is TR plus TD, which is 0.006 plus 0.05, which is going to be 0.056 seconds. Let us try to plot this on a pressure time curve. So, the value, it rises at 0.006 seconds and the value is about 33.952, which you can see from here, and then it drops off and that becomes 0.056 seconds. Let us talk about the rear wall. For the rear wall, drag coefficient CD is taken as minus 0.4 and the equivalent load coefficient depends on LW by S. In this case is 20 by 5, which is 4, for which from the CFC chart one can find CE as 0.88. So, I can now work out equivalent load over pressure, which is given by Ce of PSO plus CD of Q0. Ce is 0.88 and PSO is 40 plus minus 0.4 into 5.12, which gives 33.152 kilopascal, and time of arrival, because the rear wall will have a time lag with that of the front wall. Therefore, we call this as time of arrival, which is BL by U, which is in this case 20 by 398.172, which is 0.0502 seconds. Once it arrives, it rises. Therefore, time rise TR is actually S by U, which is 5 by 398.172, which is 0.0125 seconds, and duration TD is 0.05 seconds. Therefore, total positive phase duration T0 is TR plus TD 0.0125 plus 0.05, which is 0.0625 seconds. Let us try to plot this on the pressure and time scale, and we know that it rises at about 0.0125 and then completes at 0.0625, and the pressure raised was actually equal to 33.125, which you see from here. So, that is how the load can be calculated on different phases of a building module of an offshore platform, whose dimensions are taken as a dimension of a bluff body. So, friends, in this lecture we understood how to compute the blast wave loads on all the 4 sides and roof of the interfering structure. We have understood the governing equations and the parameters to compute the peak overpressure on all the sides, front, side, rear wall and roof of the body. We have also worked out an example to estimate the loads on different faces, different sides of a building module. So, interestingly friends, we are now able to understand how the blast loads can be computed on bluff body or body interfering with the shock wave propagation when the shock wave propagates in horizontal direction. The propagation takes place of course in multi directions, but we will try to work out one direction at a time, and we then take the optimistic value for the design purposes. Further in the continuation, we will talk about the material strength. And the response criteria of building modules when they interfere the shock wave propagation. We know that flexible structures due to large compliancy and relative frequency with respect to the blast wave frequency will attract lesser blast wave loads. So, the dynamic effect plays a very important role on the material strength of the members. So, this enhances rather the structural strength to withstand blast wave loads. Structures or building modules exposed to blast waves undergo plastic deformation because that is required to absorb the explosion energy. And we do agree that when a building module undergoes plastic deformation, there is a permanent deformation or displacement caused on the member, on the joint, or at the interconnection points where tentatively plastic hinges are formed. So, they undergo large rotational deformation in addition to the translational deformation, which is essentially caused because of their compliancy, or I should say flexibility. If you look at the material response, material cannot respond at the same phase or same rate as that of the load which is applied, because there is absorption of energy which we call dissipation resulting from deformation. So, there is always a variation between the rate at which the material responds compared to that of the load applied rate. So, result of which stress level at the yield point increases and ultimate stress point is reached to result in rupture. So, interestingly, increase in strain rate leads to strength increase because of ductility. So, it means that members develop resistance to the applied blast loads in excess of their static load capacity. So, this is accounted in the design of blast loads using a factor called DIF, dynamic increase factor. Let us try to look at the resistance deflection function of the material. In general, consider the flexural response of a ductile material we know that stress rises in direct proportion to strain. Since resistance is also a function of stress, it also rises in proportion to strain. If the extreme fiber in the cross section reaches the yield value, then the stress strain relationship becomes non-linear. On the other hand, if I try to plot the variation, I call this as the deformation and resistance. Let us say initially it is linear, then it is more with large deformation, and then it is having infinite deformation. So, we agree that this is my yield strength and this is my resistance at yield, and I can say now this is my ultimate strength or resistance and this value is my yield point and that is my maximum value y m, and strain energy of course is the area of this curve. This gives me strain energy. So, when the extreme fiber reaches yield value, interior sections or interior fibers also start yielding. We call this as section plasticization. This will result in formation of plastic hinge at the sections where all fibers or all layers along the section completely yielded. At this stage, rupture will be initiated If you look at the elastic resistance, this is the level at which the material reaches yield value, and this generally occurs at the location or at the section where moment is maximum. Beyond the first yield, plastic regions are initiated and the member undergoes a permanent deformation. So, friends, this characteristic changes with respect to the yield property or the material behavior under this kind of loads, and the rate of loading and the strain rate are not similar because of the delay taken by the material, which depends on its energy absorption capacity, which we actually call the plastic resistance capacity of the section. We will discuss them in detail as we keep on proceeding with different kinds of load resistance analysis. So, friends, in this lecture we worked out the blast wave loads on different parts like the front wall, the side wall, the roof and the rear wall. We also solved an example to estimate the blast wave loads on a building module. We also understood the dynamic material characteristics which enables the material to resist the blast wave propagation in terms of energy dissipation, and we also understood that the strain rate happens in the material is not at the same level as that of the rate of loading occurring because of the blast wave. Thank you very much.